Hey, good afternoon, everyone. Thanks so much for being here. My name is Will Benton, and I'm a software engineer at Red Hat. Today, I'm going to talk about a few aspects of some work I've been doing recently to make sense of log data with Spark, dealing with external data sources, feature engineering, finding outliers, and implementing a scalable learning model in Spark. So in the last talk, we had sort of a mix of people who considered themselves data scientists and people who do not consider themselves data scientists. Can we nod if that's still the case? And we can't really, can we? But I'm going to assume that we have something in this talk for everyone. It's not too technical and it's not too introductory. I want to start by talking about why logs are interesting. If you use computers, even if you just use one computer, then you have log data. This is a problem domain that's been well served by query and dashboard solutions, where you know what question you want to ask and you know how to get an answer. But it can be tricky to train predictive models from this kind of data. Logs are not explicitly structured. They come from many sources, and they can be rich. And they've only gotten more so in the past couple of decades as we've gone from single-node, monolithic applications, where we have maybe a web server, a database server running on an operating system, to distributed microservice-based applications where every single component in a contemporary application might be generating as much log data as your whole system would have at the turn of the century. And when you consider that you might have a whole bunch of these applications running in your data center at any given time, you really could be dealing with a lot of this data. So I'm going to talk about the system we have for storing these data and talk about how we get log records out of it and into Spark. Some of my colleagues in Red Hat's performance engineering group maintain a really great internal infrastructure for collecting, aggregating, and querying log data. There are a few components to this. There are collectors that take logs from source machines and convey them across the network. Depending on where we're running, we're going to use FluentD, rsyslog, or Logstash. We have normalizers, which take raw log data and impose some metadata and other data hygiene standards on them. One of the interesting things you have to do with actual log records is standardized timestamps, because you're dealing with hardware machines, some of which have hardware devices that generate logs, some of which have innovative treatments of things like time zones and leap seconds. And then finally, we store all this warehouse data in an Elasticsearch instance, which is great because it supports point queries and dashboard-style visualizations with Kibana. So we have a whole bunch of warehouse data in Elasticsearch from hundreds of internal machines, including cloud infrastructure, application infrastructure, machines that run QA tests, machines that run performance evaluation experiments, and even individual workstations. For my work, I actually took the data out of Elasticsearch and archived it to Parquet, and I used that to support training predictive models. Now, you should note that there's no reason why you couldn't connect Spark directly to Elasticsearch, but we saw really big speedups when we took the data out of Elasticsearch, which was in another data center from our Spark cluster, and put it in the same data center. In any case, wherever you're getting external data from, if you're dealing with a lot of it, you're going to have to do some further normalization. So how many of you have developed applications that have had to deal with streaming data, or even more than just a couple of months of aggregated batch data? So people with your hands up, you know where I'm about to go here. No matter how great of a job your data wranglers are doing, you still need to clean things up before you can even examine all of this at once. Schemas change with new requirements by design and simply with new versions of system components. Now, fortunately, there's a pretty easy sort of first pass at this. You can just sort of take the intersection of everything you have. And in Spark, this winds up being really simple. You can look at a data frame, look at the inferred schema, flatten nested schemas to flat schemas, and then just take the intersections of all those fields you have. This is like 20 lines of code. I'm not putting that code on this slide, but it's 20 lines of code. And this leaves you with a lot of interesting fields, even if you go over a bunch of different sources over a long period of time. You have the sort of classical log metadata that you might think of, like a timestamp, a severity, the host, and sort of geolocation and network address information for that host. And then you also have some additional metadata that was added in the normalization process, maybe like the environment variables from the service or machine that generated the log, an application name, a facility name, some additional metadata. Now, once you have a consistent structure, you can actually write a data frame query that operates on all of your aggregated log data. But having a consistent structure is only part of the problem. The other part of the problem is making sure that you don't have spurious null values in here. If you have data from multiple sources and Spark is going to infer a schema for it, it's going to infer a necessarily permissive schema. It's going to be the broadest schema that can accommodate everything you have. So there will be some records that have fields with null values. Unfortunately, if you're dealing with a lot of other libraries that you want to have operate on these data frames, those aren't necessarily going to be coded defensively to deal with nulls, so you're going to want to sanitize those out before you send them to the external code. But this is something that's pretty easy to do with data frame operations. Okay, we're finally at the point where we're profiling data, doing some exploratory programming. How many people have done stuff that looks like this on this slide before? Great, so on the top row, what we're doing is we're looking at severities. We're saying, what are all the severities I've seen in my data set? This is a great way to sanity check. Right? On the bottom row, we're saying what applications generate the most of each kind of log message at a given severity. So in particular, if you've written code that looks like the code on the top left here, where we're taking a data frame and we're turning it into a typed RDD, how many people have done that? A couple. Okay. So some of the rest of you are about to learn something that will prevent you from pain that other people have memories of. This new datasets API that was introduced in Spark 1.6 and is improved in Spark 2.0 lets you write programs that benefit from type checking, like RDD programs, but also from query planning, like data frame programs. And I really like query planning because it enables dumb code to run faster, and I really like type checking because it prevents really dumb code from running at all. Especially if the alternative is running for a few hours and then crashing. A really nice and simple side benefit of datasets is that they make this kind of code totally painless to write if the thing you're converting to is a collection of strings, numbers, or case classes. You can replace that manual mapping with something that looks like that. You have to make sure that the thing you're converting it into is declared in your program and that you don't just declare it interactively. But since most of you aren't doing this now anyway, that's maybe a detail you're not interested in. So we have our data in a format that Spark can easily work with. We've done some initial exploration. Let's look at how we can go from these structured log records to something that we can train a predictive model on. For most of the classical machine learning algorithms, this means having a bunch of vectors or matrices of floating point numbers. Right? Now, some of the features we might get out of our infrastructure data, like if we had a normalized rate, that has an obvious and natural interpretation as a floating point number. But other things like severities and host names, where you have one of several elements in a finite domain with no real obvious ordering or numerical interpretation, are a little trickier. So we'll start by looking at those. Who here has used one-hot encoding before? Okay, so this is a classic technique for doing this with small domains. It basically takes a finite domain of things. In this example, we have colors on the left and breakfast foods on the right. And it takes a finite domain with n elements and turns it into a vector of either n bits, where exactly one bit is set, or n minus 1 bits, where at most 1 bit is set. And there's an encoder to do this in Spark's ML pipelines library. In this case, we developed n minus 1 bits mappings for a color feature and for a breakfast food feature. So in the case of colors, we see red is 3 zeros, green is the middle bit is 1, and the other 2 are 0, and so on. And we have a way to turn collections of categorical features into vectors, which we can then use to train models. Now, whether you want to use the n-bit encoding or the n minus 1 bit encoding depends on what kind of model you want to train, but the one-hot encoder in ML pipelines will do either. So now that we have a vector of numbers instead of a log record, we can talk about how similar things are. There are a few ways to talk about similarity. We can think about set similarity, which is sort of an obvious thing we can look at. But often we're thinking about geometric notions of similarity. Euclidean distance, for example, very easy to calculate, easy to understand. Manhattan distance, very, very interesting if you're walking around a city that's laid out on a grid, so not necessarily here. And then finally, angular similarity. If we consider vectors as sort of angles from an origin, how similar are the angles that they represent? And this is really good for binary vectors, especially sparse binary vectors. So that's sort of how we can look at this metadata that we've one-hot encoded into a long string of bits. But there are some other interesting features we might want to consider with log data. I'm just going to talk about those quickly. The first of these is the distribution of log record inner arrival times. We can think of this per host, per subsystem, per service, and we can recognize that something's happening to our system if log records start arriving significantly more quickly or significantly more slowly than they have in the past from a given component. Another feature is one that those of you who've dealt with data that have both natural language components and user-supplied metadata often have to deal with. The metadata don't always align with the data. You see this in restaurant and product reviews where people have nothing good to say about something but give it an excellent rating anyway, or where they speak highly of a place but rate it poorly for some reason that's unlikely to be relevant to you. And it's really no different when a program is generating the data and the metadata, because unfortunately programs are still written by humans. So sometimes things that are routine are marked as important alerts, and sometimes things that are marked as routine are really emergencies. And if you've ever spent a lot of time reading logs, you've probably seen open source projects that inappropriately escalate the urgency of their messages. We once saw a project that actually logged everything as error, which is sort of the project that cried error, right? So fortunately, we can do some things to make sense of natural language in logs too and get features out of those messages. But it takes a slightly different approach than if we were dealing with conventional prose like we would be in product or restaurant reviews. It's outside the scope of this talk, but if you're interested in seeing more about how to make this work, I'd encourage you to check out this link where I sketch out a pre-processing pipeline for using Word2Vec with log messages and have some sort of cute results. Okay, I want to talk now that we have a way to sort of characterize logs. How do we look at the structure of our logs as a whole? How do we figure out what the exceptional things are? And to do that, we're going to have to talk about how we think about data in multiple dimensions. Now, for me, it's pretty easy to think about data in 2 dimensions or 3 dimensions because I can think about points on a plane. It's sort of natural. Points in space, you know, maybe kind of clumsy, but you can still sort of think about how those work. When you get to more than 3 dimensions, my intuitions start to break down. Yours probably do too. The log data I was looking at had about 900 dimensions. Now, fortunately, most real-world high-dimensional data only has a few truly meaningful dimensions. And it's easier for computers to find patterns in a low-dimensional representation, just like it's easier for humans to find patterns in a low-dimensional representation. So we should really use some techniques that cut down those unimportant dimensions and leave us with the interesting ones. So here's one approach called PCA that basically the idea is to find a transformation from a matrix to another matrix, a smaller matrix that preserves uncorrelated and high variance features in the source, but discards sort of low variance ones. And this is available in Spark. It's a very old technique. It's relatively efficient to compute for large data sets, and it takes a 10-dimensional data set and turns it into something that looks like that. If you apply this to actual log data, you get something that looks a lot like clustering. This is real log data run through PCA. The colors on the map correspond to severities. There are a few downsides to PCA, but the one I want to call out as most critical, in my opinion, is that its result is not really human interpretable. You get a matrix of numbers. That doesn't necessarily tell you a whole lot about what your data actually means. It just tells you a lot about how to spread out your data so that it's spread out. Right? You want a technique that tells you something about your data or about the world. So one such technique is using trees. And the process for training decision trees, how many people have used decision trees in here? Awesome. So that emphasizes the features that best differentiate between objects and ignores features with low information content. And if you haven't trained decision trees before, think of how you would try and win a game of 20 questions, and you're sort of on the right track. Right? Now, this is a supervised learning technique, which means you need to have a label for every object. Is it yes? Is it no? Is it interesting? Is it not? But there are techniques for doing unsupervised learning with ensembles of trees that have this same property of honing in on the most important features, basically by training families of trees to distinguish between real and synthetic data and using whether the data are real or synthetic as a label. My favorite example of this comes from a colleague of mine, Eric Erlandson, who has used random forest clustering on 4,400 dimensional source data, and the training process was able to identify clusters in this data using only 4% of those dimensions. So you can really pare it down with decision trees. The last dimensionality reduction technique I want to talk about is the self-organizing map. And this is a technique that learns a low-dimensional map of high-dimensional objects so that things that are things that map to nearby entries in the low-dimensional map are likely to be similar in the high-dimensional space. Here's an example of training one of these to recognize and organize color data. We're going to start with random colors, and we're gradually going to get to sort of similar colors being nearby as we go through several iterations of training. And see how it gets sort of more saturated in the corners. It's kind of nice. Okay, so the cool thing about these is that you can also use them to find outliers in your data. Because after you've trained one of these maps, you have a collection of things that resemble the things you care about, right? In this case, it's colors, but it could also be log records, as we'll see in a second. Now, when you find a new color, you can compare it to the map. The thing that's closest to it in the map might be a really good match, like it is for these things on the left, or it might be just sort of an okay match, like this thing on the right. It might even be a really terrible match, in which case you have something, right? So what does this mean for log data? I trained a map on a sample from 2 months worth of log data from these hundreds of internal machines we have. Training a 24 by 24 map with my prototype code took about 10 minutes per iteration on a single node with 40 cores. And then I used this final map to find outliers in the entire set of log records by going through every example log record, putting it into the map, and seeing how well it matched the thing in the map that it matched the best. Most of the records matched some element in the map really well. But the things that matched poorly matched really, really poorly. And if we consider outliers to be anything where the best match is at least 4 standard deviations below the mean match, we narrow down the scope of things we have to look at quite a lot. In fact, out of the 310 million log records I considered, about 1,000% of them were outliers by that definition of outlier. Now, how many people in here feel really comfortable that they can visualize 1,000%? Yeah, I can't either, so it's the red dot on this slide, actually, is 1,000%. We can get it if we zoom in there. But the really cool thing about this is that the things that were the most extreme outliers are all things you want to know about. I'm not putting the metadata here, but I am putting the messages here because messages are what I read as a human, and these things all tell me that something that I'm depending on in a data center is broken, and I better fix it quickly. So this is a Spark Summit talk. I'm going to tell you about how to actually do these things in Spark, but I'm going to give a little background on the sort of classical technique for setting these things up first, just real quickly. The idea is that when you get an example object, and here we have a random map, you find the best match in the map, and then you sort of add that object to the nearby cells in the map, having it contribute a lot to the cells that are nearest to the best match and a little to the cells that are farther away. It's a little more complicated than that, but you basically get a picture that looks like this. So we have red, and we're influencing the cells around the thing that was most red in the map. As a consequence, things that are red will get attracted to that in future iterations. So what this looks like in sort of Python-esque pseudocode is that at each step we update every element in the map by taking the value from the previous step, adding the example we're considering, and scaling that by a decreasing learning factor, which we're going to call alpha, and this neighborhood weight, which is the distance from the best match to the thing that we're updating. So every iteration is just considering one example, and we update it. Now this is pretty easy to understand, but it has some drawbacks. For one, we're considering one thing at a time, and we're updating something. It's not parallel. As Ru talked about in the last talk, picking hyperparameters is really tricky. With this technique, you either have to randomize your examples or pick a good learning rate, or both. I prefer to not have to worry about picking the right hyperparameters, so I'm not keen on this technique even if it were parallel. But we want something we can run in Spark. So the way to do it in Spark is essentially to keep a weighted average of all the matches we see at any given iteration. So each iteration, we consider every example in a training set. And basically, we just build up an intermediate state. That's the number of things we match. We multiply that by the neighborhoods, and then we take a weighted average at the end. If that doesn't make sense, if the pseudocode doesn't make sense, we have a picture. So we start with a random map. For every partition, we consider the count of things that map to each cell in the map, which is going to be on top, and then the neighborhood, which I'm going to represent as a function from the origin, as sort of a heat map from the origin on the bottom. So as you can see in this first iteration, we're using a very large neighborhood. Every match has a large impact. And it's sort of, maybe this projector is pretty nice, but you probably can't tell that there are actually different colors in there. It's pretty blurry. But gradually, things start matching. And things start matching out in the corners at first. And this map starts taking shape and really sort of starting to look more. And you see as the neighborhood gets smaller, the counts get spread out more across the map, and we're not just mapping to things in the corners anymore. So actually implementing this in Spark, we can easily sort of aggregate intermediate weighted averages from individual partitions of the set of examples we're looking at. And if you're going to aggregate in Spark, what function are you going to use? Not a trick question. You're going to use aggregate, right? That's what would occur to me. So the way this works is you sort of calculate these intermediate states for each subset of the examples. You send them all to the driver. You aggregate them all together, and then you have a map, right? Now, this is pretty straightforward. It's pretty easy to understand. The problem is your map doesn't have to be very large, and you don't have to have very many partitions before you're taking a lot of data back to the driver, right? If you have a 3 megabyte model, which is not that large if you have high dimensional data, and you have 2048 partitions, which how many people have done 2048 partitions in a Spark job? That's not completely beyond the pale, right? You're talking about 6 gigabytes at the driver, right? So a better way to do this is to use the tree aggregate, which you often think about tree aggregate as maybe improving performance, but it also improves space performance as well as time performance. If you were in Andrew Orr's talk earlier today, you saw a great argument about how efficient memory use and good performance are closely related, and I think this is a cool example of that. So if we use tree aggregate, we sort of do some of this aggregation at the workers in a shuffle step. And so that looks like this. And then we're not having to take as many things back to the driver. We still get the same map. So I want to shift gears for just a second and talk about actually putting this into production. It's one thing to sort of actually implement a model like this, but putting it into production, you have all these other concerns, right? One of the really great things about Spark is how general it is, but you may have a situation where you need to train a model in Spark and then use it from another system. And this can actually come up even if you're only using Spark, but you've implemented a learning algorithm in Scala and want to make predictions with its models in Python or R. And this is how I ran into this case, because I had a colleague who had a component in Spark Streaming and wanted to use this model in it with Python. So here's just a quick tip, Scala specific, for actually sharing these models. Basically, the idea is your model probably has a bunch of implementation details that you don't care about in another environment. You come up with an intermediate representation that's a Scala case class that's not necessarily efficient to execute, but that's easy to convert to and from that model. And then you can use this neat trick of pulling in the JSON for S library and converting that case class to JSON for free. Now, JSON, is it perfect? No. Can you read it absolutely everywhere? Yes, you can. So if you're doing a more involved thing, you'll probably have to deal with some other components of your pipeline as well, like feature encoders and other parts of your pipeline. Now, if you're using Spark's ML pipelines, you can serialize pipelines and use them elsewhere. But again, if you're dealing with other systems, you may have to do a little bit of work, but this is a good way to get started. So I want to just quickly go through a couple of practical notes. Again, when dealing with external sources, deciding when and what to cache is hard in any program. It matters a lot more when your source is in another data center. If you're using a database just to support training models, consider exporting into whatever you're dealing with into Parquet locally and operating on that. Structured query, program defensively. The libraries you call out to will thank you for it. Memory. How many people have seen a 10-minute garbage collection pause before? How many people have seen a 1 hour garbage collection pause before? Yeah, I mean, we could probably keep going, but we won't. Compute machines with hundreds of gigabytes of memory are commonplace, but you can't create a JVM that uses all of that. Now, going forward, you'll be able to use off-heap storage in Spark 2.0, but if you're stuck on an older version, you can still sort of get around this by running multiple JVMs with smaller heaps on a single machine to take advantage of lots of memory without overburdening the garbage collector. And you can often sidestep garbage collection performance issues altogether by using a more efficient approach that doesn't require you to allocate as much memory. And then the last thing I want to just call out is this idea of really putting an emphasis on a feature engineering approach over a snappy, fancy technique, and really sort of value these approaches that train interpretable models. You know, because making predictions is only part of the value of a predictive model. The other part of the value is what it tells you about your data and what it tells you about the world that you got that data from. So thanks so much for coming. Appreciate it.
Excellent. Do I have any questions? Oh, I see a question right here.
Thanks. It was a nice talk. So one question was, you said, so the the Elasticsearch index is always getting updated because the log data is streaming in. So are you using that structured streaming API, or how much work did you invest in terms of ingesting the ELK output, rather the Elasticsearch output into Parquet files?
So the way it's structured now is we basically have one index for every day. So it sort of gets aggregated that way. And you know, when I'm doing batch training, I'm just basically taking down, you know, the n most recent days or whatever. But yeah, I think that's a great thing to look at in the future.
Hi, I would like to know about the exporting or importing part of the model.
Yeah. So basically. The idea is that if you have a Scala case class, this JSON4S library will encode that as JSON for you, which you can then load into Python. You still have to sort of implement the code to actually make predictions from the model in Python.
Absolutely.
But that's, you know.
So is it possible to, other than Spark, something like I'm just trying to use in any other software like GraphDB or I want to use an interoperable database.
Right. So I think you do. That's just a solution for sort of serializing model parameters in a sensible way.
Okay.
Actually implementing the technique to do something with those model parameters is another story.
Okay. That if that happens, really helpful to do an interoperable actually. Okay.
Any other questions? Over here.
Extending on the previous question, if your Elastic cluster is co-located with the Spark cluster, does it still make sense to export this into Parquet files and then run this, or?
It is still faster to run from Parquet than it is to run from Elastic, and especially if you're not using all of Elastic's capabilities, it really makes a lot of sense to go to Parquet even if you're local. It's not an issue of like 2 orders of magnitude. It's like an issue of 2x, though.
Thank you.
Yeah.
Do you have any cross-correlation between, do you detect some dependencies between events?
I'm sorry.
How you can detect time lines between anomalies?
So sort of correlation between different components?
Some always happens before some failure.
Yeah, so that's a great question. That's something we're sort of looking at as, you know, I think it would be cool to have a good answer to that.
All right, do we have any more? Any more? All right, let's give our speaker one more round of applause.